All right. Definition of derivative. Actually, too far. I want 4, right? Okay, so we're at 4. Continuity. All right. Is everyone okay? So let's take a look. Continuity. So now continuity means continuously. So we're looking to see if it's continuous, where it's continuous, and if it is continuous. So, I just had my pen. Did I put my pen back? Probably not. I never put it back. There it is. All right, so definition of continuity. Order the function f of x to be continuous at a point x equals c. It must fulfill all 3 of the following conditions. F of x, crap. Why does it always do that? Exist. That means that at that point, it's not a hole, it's not an asymptote, it is not undefined, it is not a jump, it is not a hole jumps. Yeah, either way. So it has to exist. The next thing, the limit. So that means for the limit to exist, the left hand and the right hand both go to, at that C, would be the same number. So this was, let's say this is going to be 5, and this one would also be going to 5. So both left and right go to the same number. So the limit has to exist, so that means a C is a closed dot, right? Closed dot, not open dot. Okay, it has to go to this, and then the last part is the limit is equal to the function. So it's a closed dot here. So on a number line again, this is my 5, this is my 5, and then it'd be a closed dot here for that graph. You would see that it is equal to 5. So if this is going to 5, this is going to 5, this is equal to 5. We had some of those problems before where it would go to, let's say it went to 5. This also goes to 5, but over here, the f of x is 6. So the limit exists, the function exists, but they're not equal. So this one right here would be an example of not continuous. So again, I talked about this as a roller coaster. If this is a roller coaster track, you have this goes to number, this goes to number, but right there at that, there's a missing track. That track is like way up here. So, yeah, it's no good. Okay, so this one right here, is it continuous? So, piecewise, you're going to have a bunch of these piecewise. So what that means is plug in the number for the first value and see what we get. So if we plug in 2 for this, I'm going to get on top, we get 3. And plug in 2 for the bottom, it's going to be 2, 4 minus 1 is 3. So there, the function is going to be continuous. And I want you to pay super close attention to this one part. This one part is going to throw it off. See this right here? That's equal to, that's not equal to. One of them has to be equal to. If neither is equal to, then it is not continuous. Okay, so this is equal to 2. This one is not. Does that make sense or no? It's kind of like if it were being a number line, it would go like this. So, and on the other side, it would be this. So my number would be 3. And this side right here would pick up again at 3. It goes to infinity. And this one right here would go to negative infinity. So it's going to both sides of it, but not including the number 3. You need to have a bracket on one of these. Okay? That's super important. Yes, left hand and right hand both equal to the same thing, and there's an equal sign on one of them. Okay, for this right here, does a oh wait no, where am I getting at in the next one? Okay, so on this one, it's the same thing. Let me see. This is going to be 3 here, and this is going to be 3 here. And is this continuous? No. Why? No equal sign. Neither of them is equal to at 2, right? This is the type of question you'll get on the AP exam. This is, do you fully understand and comprehend and pay close attention to what it's asking for and what it's giving to you? Mm-hmm. Time what? Time waster. No, it's not really a time waster. It's when you see the problem and you look at this, you're like, oh, hey, okay, is this 3, okay, and then just that little detail. Okay, so that would say, no, it is not continuous. So, let's see, I don't know, does it keep going on the same part? Where am I at? Okay, is this one at 2? If you notice in the middle, I have a number at 2. So this is going to give me, let me see, 2 plus 1 is 3, 2 squared is 4, and 2, 4, that's 3. So now, it is equal to 4 in the middle, but the right hand is going to 3 and the left hand is going to 3 also. So, yes, no, maybe. You guys, please ask questions, do something, because y'all are falling asleep on me. Are you good? You're doing everything but snoring. So this one does not exist because it is equal to a different number in the middle. Okay, jump discontinuity. So a jump means the limit from the left is not equal to the limit of the right. So let's say the limit of the left is going to 4 and the limit of the right is going to 5.
Mr. Pachi?
Yes.
I have a question about the last one.
Yes.
Why do they say it does exist? The answer.
What part?
What? There's only
Where?
This is
Right
one.
here?
Yeah.
What exists?
The
It's equal to 4. Okay. The limit, okay, the limit here, left hand is equal to 3. The right hand is equal to 3. But because the two limits are the same, the limit exists, right? But now is the limit as x approaches 2 of f of x, so that's going to give me 3, right? Is that equal to f of 2? F of 2 means plug it in right at the number 2, right? So this says, this gives me 4. That's 4. So the limit does exist. So the limit is 3, but the function is 4. So is the limit equal to the function? No, they're not equal. So it says right here that the limit does exist, okay? Condition 3. Is the limit equal to the function? We have 3 and 4. Because these aren't equal, the answer is no, and the function is not continuous. Okay? So yes, good question. All right, so again, here's the jump. So think of that roller coaster track. These things, so if you were a little Mario on the little running thing and you'd have to jump from one part to the other, it's not continuous. Okay, if you have to jump, it's called a jump. Okay. All right, so here's an example of a jump. So left side goes to this value, it's equal to A, there's my closed dot. And the right side goes to some number above here, which is not equal to though. Okay, now, can it be equal to on both top and bottom? No, why? That would not be a function because it would fail the vertical line test, right? So it's not possible to have a equal two separate values right here, right? So that's another key thing that you guys should look for if you're looking at a graph. It can't be equal on both top and bottom, right? So that means a would give you two separate values. So, all right. Now, the next thing that we're going to have, point discontinuity curves when a curve has a hole from a missing point because a function has a value at that point that is off the curve. In other words, the function is not equal to the limit. That's just what we had on that previous one. Okay, the function is not equal to the limit. So we had the limit equal to one value, the function equal to a different value. So it's only at that one spot is going to have a hole. So your track is going to have a hole right there, right? Okay. Here's an example of what it's going to look like on a graph. We have a hole with a dot somewhere above it. There's a, and essential discontinuity curves when the curve has a vertical asymptote. Vertical asymptote. So let's say the limit is going up to something here. So here's one. I have a vertical asymptote right here at whatever value. Yes, the left is going to infinity, the right is going to infinity, but the asymptote is MC Hammer of math. Yes, can't touch this. It cannot equal, right? So, if it cannot equal there, then the limit cannot equal the function. If the limit of the function goes to infinity, right? So, we're saying that the limit as x approaches c of f of x goes to infinity, but then f of c, okay, does not exist, right? Or undefined. Asymptotes are when you see that undefined somewhere in there. So the limit is not equal to the function. So they're not equal to each other. Not equal. Okay, here's examples that you'll see on this. Now, a removable discontinuity occurs when you have a rational expression with common factors in the numerator and denominator. Because these factors can be canceled, it is considered removable. So we did a bunch of these where it would be like a x minus 2 over a x minus 2 and a x plus 4. So in this occasion right here, I have a discontinuity where my denominator would be equal to 0, right? So that would be, there would be a discontinuity at positive 2. So that would give me 0 here. 0 times anything is 0. So there would be a 0 in the denominator. Right, Pitar? Yeah. So there's a 0 in the denominator, but since I'm able to cancel those, I'm left with 1 over x plus 4. So now I could say, I could plug in 2 as necessary. It'd be 2 plus 4 is 6, so 1 over 6. That is a removable discontinuity at the number 2. Okay? So here is an example of what it looks like on a graph. It is just a regular line with a hole somewhere in there. So these ones right here, you're going to have some values. So we have plug in 2, that's going to give me 5. Plug in 2, that's a 5. And plug in 2, that's going to be 4. So this one right here is going to be, the left hand is 5, the right hand is 4. Okay, as x approaches 2, that means that this is going to have a jump in my function, right? Because they're not equal to the same thing, so they're going to be a jump. It is discontinuous. Okay, again right here. So this is everywhere where x cannot equal 2, right? Everywhere but 2. So right here, x is equal to 2. So when x is equal to 2, it's going to give me a value of 5. So on my graph, here's 5, and this is my 2. So that means that at 2, this is a solid dot right there. But everywhere else, it's going to be x squared. So at 2, that would be 4. So that would be, look like this. Right there. So it looked like that. So there is a hole in my track, right? There's a hole in my track right here. This one right here. Okay, here's another one, asymptote. So this one is not going to take it to infinity. So as you factor these out, these factor down to here. And because of, you could do the x minus 5. So that means that if you could do that, that means at the number 5, we have a hole, right? Because I'm able to cancel these out, I have a hole at 5. Hey, Batar. Here. Squeeze that for a while. Keep falling asleep on me, bro.
I'm never gonna fall asleep on this screen.
Oh, okay, just resting your eyes, checking your eyelids for holes. It's all right. Okay, so there is a hole discontinuity at the number 5, but as I could take the limit of this now at 5, I'm going to have, okay, so it'd be 5 minus 3 is 2, 5 minus 2 over 4, basically. So we could do a limit there, but there's also another hole or a discontinuity here. So this would mean there's a hole at the number 5, but because I cannot remove this discontinuity at +1, okay, that's going to be another value. So the graph is going to look like, crap. So as it goes to 1, so actually I want to bring up the graph on this one, because I don't see a graph on that one. If you guys got the calculators, you guys could plug it in too. You don't have to wait on me. All right, so we have x minus 3, x minus 1. Control, divide, x minus 3, x minus 5, x minus 1, and x minus 5. There we go. So now I can see what it's going to look like at 1. So at the number 5, if you notice, it looks like the curve is continuous, isn't it? It looks like the curve is continuous. Let me see. 1, 2, 3, 4, 5, right here. So it looks like it's continuous. So I'm going to menu, trace, graph. So I could actually just trace it. So at 0, it's 3. Now let's see what it, so I'm just going to plug in the number 5. And right here. So it is undefined at that point. But the graph doesn't show an open dot here. You just have to understand that from here, it is going to be undefined. But can you clearly see the asymptote at +1? Yes. So therefore, if it's non-removable, okay, you're probably going to get an asymptote there. All right. Okay, let's see. So let's take a look at this one right here. Is this continuous at 2? So if I plug in the numbers, here, so it'd be 2. 2 to the third power is 8 times 2 is 16 minus 1 is 15. And 2 times 6 is 18 minus 3 is 15. All right, so now this is equal to at 2, and it's also 2 on 15, right? Yes? So the left hand goes to 15, the right hand goes to 15, and I have it equal to, right? Yes.
It goes to 99, not 15.
99.
Oh, wait.
Did I suck at my math?
No, wait.
The 12 minus 3 does not equal 15.
Where do you get 12 from?
2
6.
times 6 minus 3.
Oh, okay. Now, this is x cubed. What is 2 to the third power?
Oh.
2 times 2,
8.
yeah, 2 times 2 is 4, times 2 is 8, right?
Yeah.
So it's 8, right? 8 times 2,
16.
16 minus 1.
15. But the bottom one.
Okay, so 6 times, oh, you're right, I messed it up. Okay, so, I don't know, I was trying to do it too quick. All right, so 6 times 2 is 12, right? There we go, 12 minus 3, 9, there we go. Okay, so, sorry. See? Okay, yeah. Trying to go too quick. So, is this one working? From this information, what type of discontinuity? This one's going to be a jump, right? So if it was at an asymptote, I would call that what? What did he call?
At the asymptote.
Okay. So we have 3 types. What are my 3 types now?
Removable.
Yeah, the removable gives me a
Whole.
hole. The removable gives me a hole. Then there is the essential, which there's an asymptote, and then there's a jump. Okay, so there's our 3 types of discontinuities. All right, so there we go there. Okay, let's see. There's just a bunch more examples of that. All right, so I'm going to give you guys about 10 minutes for this. Okay. All right, so we're going to do 10 minutes here. So 10 minutes. Let's try a bunch of these. Okay. Don't forget, like, share, and subscribe.